David here. Welcome to the channel, all about natural patterns, sustainability, and systems thinking. Today's chapter 12 of the book, The Science of Systems, How Systems Can Transform Over Time. If you want to learn more about the book, you can go to davidsugar.com/book. There you can download a free PDF of the book. Also, the paperback is available on amazon.com. You can buy the paperback and see all the images in person. So what does it mean for a system to transform over time? One simple equation is when the system of the present is transformed to a different system of the future. This is represented by a mapping here in the equation. S present is mapped to S future. Now, this mapping entails that the system is transformed, that it changes over time. And this means that the system of the future is not equal to the system of the past that has changed over time. Now, if you recall, our earlier formal definitions of a system is that a system contains elements, but also relationships between those elements. So this means that if a system is transformed from the present to the future, the elements and relations of the present do not equal the elements and relations of the future. Either the elements are changed, either the relations are changed, or both of those have changed. And there's lots of different ways that systems can be transformed over time. One example is like, consider a tank of fish, kind of like a little aquarium. Well, one way it could be changed is if you add a new fish, this could be thought of as a new agent in the system, and that can change how all the fish evolve over time. Or maybe another relationship is changed. Maybe food is added more frequently, and that can change it. So in physical systems, it's often about exchange of matter, energy, but also information is a critical piece to change systems. So we'll look at lots of different ways systems can be transformed over time. Now, there's a whole field called systems change, and that's all about using a systems perspective to understand how to make the best change. As we've seen throughout these chapters, many of the natural systems in our world are highly complex and interconnected. So just having a linear approach, just changing one piece and expecting that the other piece changes with no other effects. A more practical approach from a systems perspective to make change is from engineering. This is based more on physical information systems. And you can create these functional block diagrams. Here shows an example of an off-grid house. And you can map all the various functions, how different aspects of the system may transform the inputs to outputs, and how they all work together for a cohesive whole. So you can see in this case, sunlight and rainwater are the inputs, but all the various components of these off-grid house work together to create useful outputs for the occupants. The sunlight can be collected in solar panels, stored in batteries for electric appliances. It can also be used for passive heat to help heat the house. Rainwater can be used for landscaping, as well as stored in water tanks, purified, and used for the occupants. These functional block diagrams show how lots of different components can come together to create the overall effect. And you can see if maybe some of these pieces are missing or are not functioning correctly, it can affect lots of others. So a systems engineering is really taking a systems approach to engineering. And this is really important for very complex engineering systems, like the International Space Station, for example, has lots of different systems: air, water, electricity, communications, and they're all interconnected. So understanding all the functional block diagrams can help people identify how does the system work and how can we make it resilient to change, or if something breaks, can we have redundancy and other methods to accomplish the same goal. Another way that you can think about systems engineering is through an N2 diagram. This is shown below, and essentially this shows how different functions relate to each other. So let's say there are 4 functions. Now, it may also be the case that function 1 relates to function 2, function 1 relates to function 3, function 1 relates to function 4, and all the other permutations. So this N2 diagram maps out all the connections between the various components of a system. And you can then map how the inputs relate to outputs and also these other kind of connections in the system. So not just the function 1, 2, and 3, but how they all interrelate to one another. And for example, in airplane flight, there's lots of these different systems, the different pitch and control of the plane related to the propulsion, related to the speed. And these systems are all communicating to each other at one time. So these N2 diagrams, backed up with mathematical equations to understand it, can help provide a view of saying, how does this whole system work? All these functions are interconnected. Some may influence others. Can we map it all out, understand how it changes, and have an idea of how the overall input relates to the overall output? So this is another tool that can be used from a systems engineering perspective. Now, when it comes to systems design and designing products and services that actually work in the world, it's important to take a human-centric perspective. So the graph below shows a human-centric design process, and this is really taking a systems approach to designing solutions. Instead of just designing a solution in a vacuum, without the context of the human relationship or the social relationship of how it's used, the ease of use, does it actually solve a real world problem? The human-centric design really starts by empathizing with the various users. What are the problems? There's interviews you can shadow to understand what problems are actually facing humans. You can define those problems, and then from there you can start to develop ideas. Well, what are some ways that we can solve these problems, make effective change? It's also really useful to prototype these ideas and iterate them with feedback. And then you can test, experiment, and of course, reiterate over time. The important part here is that this human-centric design is not just designing a problem, an idealized solution that would hypothetically work, but to say, no, let's actually let people use it. What problems are they facing? Does it actually work when it's being used? So it really allows human processes to be integrated early in the design phase. And as we said earlier, this helps take a system perspective. It's not designing solutions in a vacuum, but designing solutions for facing real world problems. Now, a lot of the different change agents in the world often organize into these different organizations. And different organizations essentially transform inputs to outputs in the environment. And this can help create large-scale change. They can design engineering solutions. They often are designing information solutions. And they can create this systems change that we were talking about earlier. Now, there's a lot of different models for how to organize organizations. A very typical one is that there's a chief executive officer and then heads of different departments like operations, finance, marketing, sales. And then there's other managers and directors that report to these heads. And this allows an organization to accomplish all these different goals. When you think about it, organizations are having to juggle a lot of things. There are often human, resources. There's financial analysis, there's sales, managing, digital marketing, and all those pieces have to work together for the entire organizational throughput. Is the organization actually providing change to the environment? Is it providing value? And so systems thinking is a lot about understanding how are organizations working? Are they actually creating the solutions to help transform the problems which they are working to address. And we were talking earlier about a human-centric design, a systems-based design, and that can help catalyze and increase the impact of organizations, that they're designing solutions to real-world problems and that they're understanding, which are the leverage points to really solve these deep problems. Another way that one could understand an organization or map it out is by different perspectives. So here, this shows it's called an architectural framework model of organizations, and this was from the Treasury, the US Treasury. And essentially, they had different perspectives like the planner, the owner, the designer, and the builders. And that there's different views. Are you looking at the functional, like what is the overall throughput? What is the information? What's the key information needed? What is the organizational structure and the infrastructure? Now, these different perspectives can also have these different views. And this model identified different work products. So what is expected to be produced? It might be a builder from a functional perspective is working on the system process descriptions. From the informational view is working on the physical data model, organizational view, the physical network, the infrastructure, the performance of the actual infrastructure. But the owner may have different work products for those views. You can see in the graph, functional would be something like activity and trust model, and infrastructure would be like the systems interface. So what's important here is not necessarily these exact work products. They can change for an organization, but for an organization, there may be different perspectives. It may be administrative, business, and finance, and there could be different views. Is it for the internal success of the business, the external success, or anything else you define? And so this helps understand how all the different pieces of an organization are working together to create the overall throughput and create the overall change desired by the given system, by the given organization. Now, another interesting connection between systems thinking and maximizing the productivity and optimizing organizations is this idea of a complex adaptive system. And essentially, a complex adaptive system has the ability to adapt, to change how the system relates to the inputs, to the outputs, to essentially change the rules and for it to learn. This is similar to like evolution. And so in an adaptive learning loop, a system can change its rules, so it changes how it transforms inputs to outputs. So this view really thinks about organizations as almost living organisms. That organizations shouldn't be thought about as static entities where rules are fixed, the same inputs go to the same outputs for all of time. That's not really a good way for a business to adapt to changing environmental conditions. With an adaptive system, the organization itself can change its rules. Maybe there are new work products, maybe there's new technologies, maybe there's new systems that are being integrated. And so businesses, in order to stay successful, need to always evolve and keep up with the environment so that the inputs can be transformed to outputs within the given context. So using complex adaptive systems for optimizing organizations provides a new view. So it's not a traditional, really like a mechanistic and fixed view that only some inputs can be transformed to outputs, but this is more of an organic and evolutionary perspective, which is saying, how can we support an organization to change over time so it can be sure to meet the environmental demands as they change? Now, there's a lot of different tools to analyze a system and help make decisions for an organization and help decide what are the best levers to make change in a given system. One tool is called the SWOT analysis, and this is essentially strength, weaknesses, opportunity, and threats. And these exist on a spectrum where internal versus external And are these factors helpful or harmful for the business? And this SWOT analysis can be helpful to say, before we make a decision, let's understand the given context. This is, again, taking this systems change view, which is understanding the patterns of change and the connections within and between systems. There may be other systems that are providing helpful or harmful factors, internally or externally. And it's helpful to map those out so that stakeholders can get a shared understanding of the context and make the best decision possible. Another approach is a criteria matrix. Essentially, you can have multiple decisions, like decision 1, 2, and 3, and there could be different criteria. Is it profitable? How does it affect other stakeholders? Are there other externalities? Are there other risks that we're looking at? And so for the various decisions, you can map those all out, and then that can help make decisions within complex systems. Most organizations in the world are involved with lots of complex systems, society, finance. And so these kind of tools can help map the landscape. And it's impossible to map everything. I'll just say that, there could be an infinite number of criterias, or the SWOT analysis could go on forever. But it's really useful to say, what are the most relevant factors facing our organization or facing an individual? Write those down, get a shared understanding, and say, with the information known, what's the best decision? Now, of course, you could just analyze the world forever and ever and have a more and more detailed understanding, but never make a decision. So it does take time and energy to analyze the world, and more time and energy used for that means less time and energy can be used to actually act upon the decision. So there's also a weighting and a balancing game between how much analysis versus action. But analysis can be helpful to increase the optimization, increase the effectiveness of action. Of course, in a balanced way. You don't want to just analyze the world forever without ever doing anything. But you don't really want to just do things without really considering the ramifications or unforeseen consequences. So another approach to a system analysis is these tools called causal loop diagrams. And causal loop diagrams identify, is the relationship between two factors direct? They mean they both go up or both go down at the same time, or indirect. If one goes up, the other goes down. If one goes down, the other goes up. Now, direct relationships are represented by a plus arrow. So in this example here, you see there's prey and predator. When there's more prey, like let's say there's rabbits or something, then there could be more predators like wolves or something. So a larger prey population supports larger predator populations. And decrease of prey will decrease of predator populations. So there are direct relationships. So that represents a plus arrow. However, when there's more predators that can eat the prey. So there's an inverse relationship going that way. When there's less predators, more prey can reproduce. So what happens in this causal loop diagram, there's both a direct and an indirect. However, those work together to create a balancing effect. And we looked earlier at the chapter of flux of a prey-predator model, and essentially this idealized and simplified model shows that prey and predator populations tend to balance one another over time. They kind of go in these waves. Now, these causal loop diagrams can also be used for lots of other models and understand complex systems facing humanity. This shows a causal loop diagram for a traditional agricultural system. And I'll just highlight some of these models. So here we see that the herd size is inversely correlated with the amount of forage biomass, the amount of plants available for forage. So when there's a large herd, it decreases the forage biomass. But when there's a smaller herd, it increases the forage biomass. However, forage biomass and environmental quality are directly related. So when there's more forage biomass, then the environmental quality increases, more grass and there's more wheat. But when the forage biomass decreases, the environmental quality decreases because there's less plants. Now, this causal loop diagram shows a lot of other factors in the traditional agricultural system, and different stakeholders can come together and say, what are the most relevant factors facing us today? They can come together, put these all on a map, identify some of the relationships. Are these direct? Are these inverse? And this can help identify these leverage points. Well, if there's limited time and resources, which of these factors should I change? Is there maybe one problem? If one relationship could be changed, or one thing could be removed, or one thing could be added, could this affect the whole system, create a butterfly effect? So this system analysis really helps identify what are the most highly leveraged points to create change in the system. And also this can help see unforeseen consequences. You might add one element to address one problem, but inadvertently create a whole bunch of other problems. So this system analysis can help try to identify that. Now, I'll just say again, this system analysis can be extended out to infinity. You can always look at more and more and more factors, but now that takes more and more time and energy for that analysis, and it may be less relevant. So there's always a balancing scale of getting folks together and say, what are the most important elements to consider? What are the most important relationships between those? And from then, how can we make the best decision with limited information? We're always going to have limited information, but what's really important is what's the best action we can take for the given analysis. Now, Donnell and Meadows identified key ways to change the systems. So, wanted to run through some of these intervention strategies, and these are ways, if there's a given system with different elements and relationships between those, or stock and flows, or these causal loop diagrams, what's the best way to make change? One more simple way to make change is through altering the various numbers in the systems. And these are like changing particular constants to influence the systems. So an example of this could be like to change a tax rate to a lower or higher percentage. The relationship is already existing, it's just changing the number slightly. And this can change a system. Another way could be to change the amount of buffers to add more stabilization. So if there's some food storage that's being used as capacities in case of food shortages, increasing that buffer can provide a critical time for a system to balance, in case of more volatility. Another approach could be to add a whole new stock and flow structure. So, for example of this is consider a house with solar panels. Now, if a battery was added, a battery can create a new way to store the energy instead of going directly to the grid, and that can support the system and create a new kind of change in the system. Delays are really important in systems. Changing one aspect of a system, it may take time to change another aspect of a system. So if there's faster communication, if delays are decreased, for example, that can really change how business information is shared. If business information is shared more quickly versus slower, that can change how fast people are adapting to a changing system. Now, creating balancing feedback is really a useful intervention of change. We saw the predator-prey model, which balances. So one example of this could be to say, increasing the taxes for larger incomes and decreasing them for lower incomes would help balance economic distribution and create more wealth equality. So as income increases for individuals, they'll pay more taxes to help balance this. But if income is decreased, there'll be less taxes, and this would help balance income distribution. So this is an example of a balancing feedback, and there may be some new balancing feedbacks that can be introduced into systems to help make systemic change. Reinforcing feedback is when two aspects are reinforcing one another. So one example of this is to basically use the monetary savings from energy efficiency projects, put them in a fund to invest in more projects. So it creates this feedback loop. As more and more energy is saved, more money will go into the fund, which can invest in more energy efficiency projects. And this can create a virtuous cycle and promote change in a system. Now, these are more short-term, more direct ways to change a system. And now we'll be getting into more longer-term, more systemic ways to shift systems. So another way is to change the information flow in a system. Sometimes there's two parts of a system that have no communication between each other, even though it would be essential. So there's, as we saw last chapter in sustainability, there's a whole host of new sustainability metrics that corporations are disclosing. And essentially, this is adding new information into the market. Companies are disclosing environmental, social, and governance metrics. And now for the first time, investors can now use these metrics to help identify which decisions they're going to make, which corporations are going to invest in. Another approach to intervene in a system is to create new rules. So there could be a new rule created like fining unsustainable activity, like fishing in protected zones. And these new rules can really help dictate how different agents interact in the system and can create ripple effects over time. Another approach is to enable self-organization in the system. This can be seen with digital media platforms where agents can self-organize. They can say, oh, there's resources over here, or this area is closed due to some flooding or natural disaster. Here's support systems that could be used locally. And what's really interesting about self-organization system is that there doesn't need to be one central body to put all the information in there. Social media networks are one of these examples where lots of people can contribute, and this can self-organize over time and solve lots of different problems. Now, getting even further back and even higher level in long term, it's important to reanalyze what are even the goals of a system. A lot of times, all these systems behaviors are working towards these goals. Is the goal to increase GDP, or is it to increase income after living expenses? So changing the goal can have completely different effects of what is the system driving to. So one of this is that, what is the goals of a corporation? Is it one view maybe to maximize profits for shareholders? Or another view could be to maximize benefits for society and larger stakeholders. And those two different goals have radically different outcomes. So it's important to note that, changing these underlying goals can create a whole different effect of the systems. And in large part, these goals, a lot of the agents in the systems are, you indirectly referencing these goals, and these goals are indirectly influencing a lot of things. So by changing the goals, it can influence a lot of aspects of the system over time. Now, finally, getting into the paradigms. This is like the overall mindset, the overall goals, structures in a system. And changing this paradigm, this overall goal, this overall mindset can change what is the system even going towards? What is the overall mindset, which the system is it considered? So, for example, in an economic system, is there the assumption of endless growth, or is it, we live on a finite planet and that growth must be sustainably minded? So changing this paradigm of how we view different systems and interact with systems can create a large-scale change. And finally, the highest level intervention method identified by Donella Meadows is transcending paradigms, the ability to reevaluate our paradigms and develop new paradigms. Often, if there's some type of dogmatic system where saying no new goals, no new paradigms can be considered, that means the system can't evolve over time. Nature is always changing, so we must also change our paradigms over time to be able to fit into our context. Now, one of the most widespread aspects of a paradigm is the scientific paradigm. And this book has been a lot about science, so really wanted to touch on how scientific paradigms change over time. And this was also written about in the book, The Structure of Scientific Revolutions by Thomas Kuhn, identifying how scientific paradigms change. Often there's some early adopters, and then it gains traction, and there's more and more evidence, and then there's widespread adoption with a new paradigm. For example, there was, Newtonian physics, and then relativity and quantum mechanics was a new paradigm which was adopted over time. Now, how are these new scientific paradigms and theories constructed? A lot of times this occurs by observation. There are observers in the world essentially observing real systems. What kind of data are we getting from looking at nature? Now, observers, we can postulate different models, different formal systems about how can we understand this world. This may be a scientific model. This could also be other models like economic models, business models, any kind of analysis to understand what's going on. And then those models can be tested to say, is this actually matching what we're seeing over time through, experimentation? And then this cycle can continue. And so through this cycle, observers can gain more knowledge about nature to say which models help provide a more accurate description of real systems. And, there's no proof to say this model is exactly what the real system is. All that we can do is say this model is better than other models. It's more efficient at predicting, what happens, and it's a more accurate case of what's really going on. So this is done in a scientific context, but also business and politicians and lots of other people are constantly modeling the world and constantly adapting. So changing paradigms is really essential to, keep up, to evolve, because real systems are also changing, right? They're not always the same. So our models themselves also need to change. So over this book, we kind of reviewed lots of different scientific paradigms and wanted to show a snapshot of some of these overarching scientific paradigms over time and kind of this adoption curve that we mentioned, where first there's some early adopters and then there's widespread acceptance. One of the first things that we talked about was Newtonian physics, and this was really one of the first attempts to rigorously apply mathematical models to understand nature's patterns, more about trajectories and gravitational bodies. There was also thermodynamics, understanding like steam engines and some initial aspects of entropy, and this provided more and more tools. Now, relativity and quantum mechanics provided this new paradigm of physics. Now, it didn't say Newtonian physics is wrong. It just said Newtonian physics is a limited subset. When not moving fast to the speed of light or not at scales really, really small, quantum mechanics simplifies into Newtonian physics. So that's right in a way, but there's a broader theory of essentially that when moving near the speed of light or being really, really, really small, there's new properties that come about. So there's this whole new paradigm of relativity, quantum mechanics in the 1900s, and we were reviewing some of those new aspects like wave-particle duality, the measurement problem, lots of other things like that. Now, in the 1950s, there was also chaos theory was developed, and a lot more about computation. We're looking at like Shannon entropy and like the early computational systems, which really started the informational age. And so some really interesting aspects of this is in chaos theory, even if the different components have a rigorous mathematical model for how they work, like three bodies under gravity, it turns out that a lot of these systems can't be predicted over time. Even three bodies under gravity, there's no analytical solution to predict all future states. You have to put it in a computer and see what happens. And so this shows that most of the systems in the world, practically every system except for some simple cases, are chaotic cases. So this really showed limitations. We can't just predict all the patterns in nature. Most of the patterns in nature are highly complex. There's like this butterfly effect, highly sensitive. So this is a kind of a new paradigm of showing that there are like these hard, strict limits. Even when using Newtonian physics, in three bodies, there's limits to what can be known about that, what can be efficiently computed. You can put three bodies in a computer and see what happens, but often that has to be run to infinity to see, the end result, and there's no shortcut, essentially. Now, I wanted to highlight this other critical paradigm, and there's many other paradigms in other fields that are not on here, so this is by no means a comprehensive list, just some interesting aspects I wanted to highlight, is sustainability. And sustainability science, in a way, is a new paradigm of science because it's saying society and humanity is not separate from the globe. Humanity's infrastructure and systems affect the world on a global scale. And so climate change is an example of showing how human-caused emissions can affect the global climate. So in the new sustainability science, we really have to understand humanity as society as part of the world, and we have to design sustainable solutions with that in mind. So I just wanted to highlight that as a whole, systems science, systems theory really helps synthesize a lot of these new paradigms of science. Systems thinking is a lot about complexity, connectivity, and these cybernetic systems like informational and living systems. And so it's not just about understanding the world as discrete parts, but really complexity, interconnection, and emergence. So wanted to highlight some of the key paradigm shifts that a system view presents. So we started the book really highlighting the difference between a more parts-based views, understanding the world as different isolated parts that are more linear, versus a systems-based view, interconnected parts that are non-linear that can create emergence. Now, there's been some scientific evidence to change some of these assumptions and views about how nature works. In a parts-based paradigm, it's often viewing the world as these isolated components, like isolated particles. But as we've seen in quantum mechanics, a particle can only be defined when it's interacting with another particle. Otherwise, it could be in any probable place. So the quantum wave collapse really points to this idea of a relational identity, that things are defined in relation to one another, not in isolation. We were talking about the three-body problem. Essentially, a parts-based view, a linear view of systems, is that the whole is just the sum of the parts. But in chaos theory, the properties of the whole can be different than joining the properties of the parts. And there can also be chaos and the inability to easily predict. Now, we're looking at computational reducibility, so the ability to make efficient predictions, to have a problem and to reduce it to a yes or no decision. However, we were looking at some of these uncomputable numbers a few chapters ago, and there's a lot of computational functions that are not reducible, that don't converge to one number over time. Similarly, the three-body problem has to be run to infinity. It can't be easily reduced for a decision problem for a yes or no answer. Now, earlier in the book, we're looking at the Gödel's incompleteness theorem, which was that the notion of first-order logic, like math or arithmetic, one may think it's complete meaning that every true, outcome can be proved, but it turns out it's incomplete. So there are statements that are true but can't be proved. And this is really showing a very open-ended view of science and math, that there may be things that are true but can't be proven mathematically. And this really dovetailed with the irreducibility of lots of computational problems and the complexity. Now, we were looking at emergence before and looking at biology, and there's often this case of just like a bottom-up biology where just, the DNA creates the proteins and that creates the overall effect of the organism, and it doesn't really come the other way. There's not a top-down. But we see that there's not only bottom-up, but there's also top-down influences working both ways. Like epigenetics, the environmental factors can change which aspects of the DNA are expressed. So this is showing that there's not just a bottom-up, which would be called like nurture, but also nature, the effect of nature on biology. So it's both nature and nurture. It's not nature versus nurture, right? They're bottom up and top down are both working together. And finally, we're talking about this perceived duality between humans and nature. But now climate change and all our resource limitations, we're realizing that humans and nature are interlinked in a system. So overall, this is reviewing a lot of the key paradigm shifts presented by systems thinking, and there's a lot more. But this is pointing to a new way to understand nature. It's not based on these isolated parts that are easily predictable, reducible in a complete fashion that bottom up creates everything and humans are separate. No, it's relational, it's chaotic, it's irreducible, it's incomplete. Bottom up and top down effects are occurring at the same time, and sustainable solutions must design with humanity and the earth in an integrated fashion. Thanks so much for tuning in today. This was the final presentation about the science of systems. So if you want to get the book, you can download a free PDF on the website, davidsugar.com/book. Also, you can get the paperback on Amazon. Thanks for listening to these various overviews of the chapters. And going forward, I'm going to be doing videos on select topics and other interesting things about sustainability, natural patterns, geometry, lots of cool things. So if you're interested in the channel, please subscribe and you'll hear more from me soon. Thank you.